Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Coding 101 is provided by CacheFly at CacheFly.com.
This episode of Coding 101 is brought to you by lynda.com, the online learning platform with over 3,000 on-demand video courses to help you strengthen your business, technology, and creative skills. For a free 10-day trial, visit lynda.com/C101. That's lynda.com/C101. And by DigitalOcean, simple and fast cloud hosting built for developers. Deploy an SSD cloud server in 55 seconds. Try it today for free. Visit DigitalOcean.com, and once you sign up, be sure to enter the promo code C101 in the billing section for a $10 credit. Today on Coding 101, it's a wild card episode with Steve Gibson. Hello and welcome to Coding 101. It's the Twitch show where we let you into the wonderful world of the Code Warrior. I'm Father Robert Ballas. Lou Maresca is out for the day, but we're doing one of our wild card episodes. For the folks who are new to the show, this is our opportunity to stop between programming modules and actually speak to the people who are making the products that we want to use, who are advancing the state of the programming art. And we've got a great guest, a man who we've had on the show before, Mr. Steve Gibson. That's right, the security guru for Twit TV. Steve, star of Security Now with Leo Laporte, thank you very much for coming onto Coding 101.
Hey, Padre, it's absolutely my pleasure. We had a great 3 shows with you subbing in for Leo while he was on vacation, and so I'm happy to join you over on this one.
I got to say, I'm happy that Leo's back because that man does so much work here. I don't know how he does as many hours of broadcasting.
There's no replacing him.
There is no replacing him. No. But I do like when he goes away because it does mean that I get a chance to actually sit down and chat with you. And that's the most fun 2 hours of security geek out I will ever do. So thank you.
And our listeners love having you as a co-host. So that works for everybody.
Yeah. But the reason why you're here on Coding 101 is we had a chance in an episode of Security Now for you to do a catch-up on SQRL. Now, if people haven't been watching Security 101, SQRL is something that you've been working on. It's an open source, I'm going to call it a movement. It's no longer a project, it's a movement. It's people who have recognized that our system of passwords, our system of authentication, our system of carrying identity from system to system is broken. I mean, would you agree with that? I mean, it doesn't work anymore. It's breach after breach after breach, and we don't have a really good way to make sure that our credentials stay safe.
When you think about it, nothing has changed since before the internet. Once upon a time, there were mainframe computers, and people hooked terminals up to them because they had time sharing, because these mainframe computers were so expensive, they had to keep them busy all the time. So they hooked them up, they hooked individual terminals up, and they gave users accounts on the mainframe computer. And the way the users identified themselves is with a username and a password. And this is decades ago. And when the internet happened, we didn't fix this. We didn't change it. And in fact, what happened was a model that you might say, okay, well, that works in a mainframe with terminals because it's an enclosed ecosystem. There's no, it's like, it's on elevated flooring with air conditioning. It's just one machine, and there's security that's sort of inherent. Well, so now we stick all this over a network, which was never designed with security in mind, where security was added afterwards, and where everybody's in a hurry, and they're getting systems, and their bosses are putting pressure on them to get this thing online. And mistakes are being made because these systems are incredibly complex, vastly more complex than they were back then. And consequently, people's credentials escape. So we're still using a system that hasn't evolved in decades, despite the fact that the world in which we're using it has completely changed.
I would absolutely agree with that. And I really want to draw out something that you said, which is security was added afterwards. That's something that we see again and again and again, which is even when we consider the internet. The internet, when they created it, they never thought that that first protocol, that TCP/IP, was going to be the thing that everyone would be using, because otherwise they would have designed it better. They would have designed it with security. It was sort of like, this is our draft. This is our way to make sure that this thing actually works. You should take it and make it more secure. And that taking it and making it more secure never happened.
Well, when the guys that actually developed these protocols have been asked what they think they did wrong, because I'm in awe. I mean, like, if I have heroes, it's the guys that designed these protocols so long ago, which we're still using today, because they had such foresight. They were so robust in the way they designed them. But when asked, what do you wish you did differently? The number one thing, the mistake they feel they made, is that they never designed security into the underlying base technology. There was no privacy. The whole SSL, the secure sockets layer, it's called that because it's a layer on top of the existing sockets. You know, the IP and the port number together form a socket, and in Unix terminology. And this was added by Netscape when Netscape, that, you know, what was the early predominant browser, said, you know, if we're going to ask for people to trust this system more, to do things where eavesdropping would be a problem, like entering a username and password, we need to somehow keep that from being easily sniffed. I mean, so privacy wasn't in the original design of the internet, and the guys that put it together wish that they had put that in from the beginning. They feel that was a mistake.
Now, Steve, I know that there's going to be people who are watching the show right now who are going to be saying, this is all fascinating, but why isn't this in Security Now, or why isn't this in Twite? I mean, it sounds like that would be a better show for it to be in. But the reason why I've asked you to come on is because, specifically, since we know the last time you were on, you talked about this idea of having foundational knowledge of the technologies that we're using. I want you to talk about some of those foundational issues that make it difficult to add security in the things that we program. But before we get to that, I do want to give you some time to talk about SQRL, because I find it's a fascinating project. I really do think that it has legs. I think if it gets enough traction, if it gets enough people who will adopt it, who will use it for authentication, it could have a big difference on security. Could you explain to the folks at home, in as layman terms as you possibly can, what is SQRL? When you talk about this new authentication system, what does it do? How does it work? What would you need to be able to implement it?
Okay, so at the top level, and after I do that, you could tell me if you want us to go any deeper. But at the top level, SQRL is a public key based authentication system, and we don't have any of those yet. Even one-time passwords are not public key based. They're private key, where you have a secret which is generating a sequence of digits over time, and you depend upon that secret being kept. And the secret has to be kept by a third party, typically. SQRL is a public key system which has a huge number of benefits. At sort of from 10,000 miles up, what SQRL allows you to have is a single identity, which is internet-wide, which you may never have to change in your entire life. Your identity is like a Bitcoin identity. It is, in fact, 256 bits, which are obtained at random, just like a Bitcoin address. So that is a single, unique combination of bits, which is made for you by a SQRL client. And if everything goes well, you never need to change it ever, because it is never exposed. It cannot be lost. There are provisions if it got hacked from you for for essentially recapturing and recovering your identity. But imagine a single identity, just like there's only one of you. So there's a single identity. As you go to different sites around the internet, through the way the SQRL protocol works, a combination of that unique identity and the domain name where you're visiting produces another value, which is actually is your public key by which that site knows you. And every site you go to gets a different unique public key. So that means you cannot be tracked as you go around the internet because there's no way of linking these individual public keys together. And a site that you visit can challenge that you are who you are claiming to be, that you are the owner of this public key, by giving you a random blob, which it has never given to anyone before and will never give again, and challenging you to sign that using the matching private key for that site. So you return the signed blob and the public key for that site, and so the site is able to verify that you are still identified by the same public key and that you have the matching private key that goes with it. So, and in a nutshell, that's the system. So what this means is that we are giving, for the first time, websites no secret to keep. We're just giving them a public key by which they recognize us when we come back. And if they lose it, if they lose their database, unlike now with usernames and passwords, it doesn't matter because that database of public keys is of no value to anyone else. And it cannot even be used to impersonate you because you have to prove you have the matching private key in order to assert your identity. And the private key never leaves the SQRL client, which is able to regenerate every time your identity visits the same site. So in essence, it's a simple system, which is why I think it has a chance of succeeding. The protocol is open, every aspect of the specification is open and published, and we've got people independently implementing SQRL clients and servers to be both ends of this connection. And the last cool thing about it is there is no third party. In this post-Snowden era, nobody is going to trust us or trust a third party to hold our identity for us. What we want is a two-party solution, just us and the site we're visiting. And that's what SQRL is.
There's going to be people out there who are going to say, oh, so it generates really, really hard to guess passwords. And no, what I love about your system is it stops a vector of so many breaches, which is someone breaches a poorly constructed database, a poorly constructed site, and then tries those credentials against every other site they can find. And you'll find some users who have reused credentials over and over again, and now you've got a breach. With this, because the blob that any particular site stores is absolutely useless on any other site, that's dead. That vector of attack no longer exists, which I think, that's hard to do. Let's talk a little bit about this blob. How do you generate the blob?
Okay, so that's really an interesting aspect that really fits, I think, with Coding 101, and that's the challenge of randomness. The problem is that, as we know, when they're functioning correctly, computers are not random. Computers are deterministic. They execute instructions in an absolutely determined sequence, and every time you add the contents of two registers in the CPU together, again, given that it's functioning correctly, you're going to get the same result. But now we want something unpredictable. For cryptography, there is a huge need for unpredictable data. Data which, like as I was explaining in the case of this blob, our requirements for it are that it be unique that it has never been generated before, it will never be generated again, and that software which is all about reproducing the same values over and over and over can be used somehow to produce values that are completely random. Now, in the case of this blob, where it's never been generated before, it's going to be generated once and then never again, there is a simple way to do that actually doesn't require a great deal of entropy, of randomness. And that is, a site like Amazon could pick, with a good source of randomness, a cryptographic key. And then they would simply encrypt a counter. So they would have a counter which is counting up one time for every time they issue a blob, or in cryptography we call it a nonce, which is a number used once, N-O-N-C-E. So Amazon would have a secret key which they use with a cipher like the Rindal cipher, AES. And they would simply be encrypting a counter, and that would produce a sequence of output such that as long as the counter never repeats, and it's easy to make a counter not repeat. Every time you increment it, you store the new value in non-volatile memory, and if you reboot the server, you pick up where you left off. So we call that a monotonically increasing value in programming, so that it goes up, it increases in an upward direction, it never drops back down. It's monotonically increasing. So we simply encrypt that with a secret key that never changes, and what we get out from a good cipher is an absolutely unpredictable bunch of gibberish where there's no relating the two. No one can predict from any sequence of them what the future holds. And because the input is an increasing counter, we know that we will never produce a value in the future that we have issued in the past. So that's a perfect, simple way of generating this blob where the requirements are: it has never been seen before, it's generated once, and it will never be seen again.
And that would make cryptography incredibly easy, except for one thing, and that is it's actually very hard to generate a random number, a true random number. Why is that? I mean, yes, computers don't operate on randomness. Computers operate on specific instructions that you give it, which provide some sort of result. But why is it so difficult for me to get some sort of random value that I could use against that ever-increasing number and come up with that truly unique blob?
Right. So, okay, again, the problem we have is that computers always do the same thing. So for true randomness, things like the weather or like look at waves lapping up against the shore. Viewed from a great distance, the waves look pretty repetitive. But when you get very close to them, they are actually what's known as a chaotic process. There's a famous example of Sun Microsystems' early attempt to generate random numbers used a room full of lava lamps with video cameras looking at the lava lamps. And they processed these video cameras to produce a stream of true random numbers, because the actual motion of the wax, the heated wax in the lava lamps, was chaotic enough and unpredictable enough that they generated when the video of those was processed, absolutely unpredictable random numbers. But that gives you a sense of the lengths that people went to in order to create something that could not be predicted. Now, in existing technology, there are two things we can do. One is to use some sort of physical process. I gave just already 2 examples. Like, you know, waves lapping up on the beach is a physical process. And if you just took a picture of that, for example, if you digitized the shoreline, you would get something that could not be predicted. And then the other example of a physical process is the hot wax in a lava lamp. Again, cannot be predicted. But those are sort of awkward and time-consuming and large. It turns out that there are electronic processes which produce uncertainty sort of at the molecular level. And one is electrons migrating across an insulating barrier under pressure. If you have a diode which only wants to allow a current to flow in one direction, yet you push a current through it in the direction it doesn't want it to allow, there is a little bit of leakage. And the leakage is actually called quantum noise. It is the success of individual electrons tunneling through this diode that is resisting that cannot be predicted. And so if you put a very sensitive amplifier on this reverse biased diode, you get quantum noise. And you can then process that in order to get true random numbers.
Steve, I do want to talk a little bit about how you've tackled this problem with Squirrel, because it's a nice bit of programming. I also want to say, way back when I was a different person, I was working with an agency that what we used to do is we would actually make recordings of atmospheric noise, completely random atmospheric noise that was meshed together with other recordings of atmospheric noise. And what you would have is you would have 2 identical copies, but they were unique. They did not exist anywhere else. They were completely random. You could not recreate them. And that's what you would do. You would have 2 chests full of this. You would send them off to different spots, and that became the cipher. That's what it was hashed with, so you could encode it on one side and unencode it on the other side. Completely unbreakable, but the problem was, of course, it's difficult to try to send physical copies of your key from one spot to another. Now, when we come back, let's dive a bit more into Squirrel, but before we do that, let's go ahead and take a break to thank the first sponsor of this episode of Coding 101. Now, folks, I know that because you're watching this show, because you're watching Coding 101, you have a curious mind. You want to know how the world works around you. You want to develop yourself. Maybe you want to learn more skills for programming. Maybe you want to have help in a hobby. Perhaps you want to do drone photography or just maybe studio photography. Or maybe you just want to help with your job skills so you can look for a better job. Well, you could do that on the internet. You can go from site to site and from place to place and expert to expert, and hopefully you'll find what you need. But if you're a smart person, you go to the one-stop shop for knowledge on the internet, and of course, that's lynda.com. Now, lynda.com is for the curious mind. It's for the maker. It's for the person who wants to do things. Lynda.com gives you everything you need to jump into the next area that you're interested in. Do you want to learn about programming? You can do that. Do you want to learn about Excel? You could do that. Do you want to learn about the next thing you'll need to jump into the next position and the next position and the next position? Well, that's what lynda.com is for. Now, right now, the courses I can recommend are Design Patterns with Python, the Essentials of Cryptography. I mean, that's exactly what we're talking about. And Network Security, C++ Smart Pointers, and C++ Move Semantics. There's also a new essential training for Eclipse, which is an industry-standard integrated development environment and a critical tool for developers who want to build projects in multiple languages, including Java, PHP, C, C++, Perl, and Python, all languages that we've covered on Coding 101. Now, of course, you probably have heard the story of how we've used lynda.com here at the Twit Brickhouse when we've made our switch over from Final Cut on the Mac to Adobe Premiere Pro on the PC. And that's great. I mean, yeah, it's good as a reference, but we've also used it as a push-off for when we have audience members who are getting into, say, know-how or Coding 101, and they want to learn a little bit more than we can give them in 30 or 45 minutes. Well, lynda.com lets them learn at their pace when they need it. And that's one of the things that I love about lynda.com. You can learn from top experts who are passionate about teaching. You can stream thousands of video courses, and you can learn at your own pace, create your own playlists, create your own notes. And my favorite part, because they've got transcripts for all their videos, it means that when you have a problem, you don't have to watch an entire series of videos. You can jump exactly to the part that has the answer for the problem you have. Lynda.com isn't just a place to learn, it's a place to store your knowledge. You can also download tutorials and watch them on the go on your iOS or Android devices. And, you know, this is actually a very social way for you to encourage your friends and your family to learn something new each day. Because if we ain't learning, we're not exercising the brain. Now, your Lynda.com membership gives you unlimited access to training on hundreds of topics, all for one low flat rate. I can't recommend it enough. And whether you're looking to become an expert, you're passionate about a hobby, or you just want to learn something new, I urge you to visit lynda.com/C101. That's lynda.com/C101 and sign up for your free 10-day trial. That's Lynda, LYNDA.com/C101. And we thank lynda.com for their support of Coding 101. Steve, let's get back to it. Now, so we are starting to hear about the difficulties of making a true random number out of what by its nature is a non-random process. How did you solve that problem with Squirrel?
Okay, so given that we don't have a true random number generator, what we need is the best possible pseudo random number generator. And it turns out that the requirements are that there be no collision among Squirrel identities. The goal is for a Squirrel client running on Windows to be able to come up with a large random, well, and I have to say pseudo-random because it's actually not random. Unless we have quantum level noise of some sort, a true random number generator, we have to settle for an extremely good pseudo-random number generator. It turns out, though, that modern computers have so much going on with them that if we harvest all of the complexity in a contemporary PC, we have enough. We have easily more than thousands of bits of unpredictability, and we only need 256. So from the moment the computer starts up, a modern multi-core processor is incredibly complex. There are performance counters which monitor things like the number of branches taken. They're inside these machines. In order to get the speeds that we're just used to now, they're doing things like speculative processing, where the cores come down to a stream of instructions, and when they hit a branch, and which is going to alter the direction, because the instruction has the processor has a pipeline, and it's actually performing multiple instructions at once, the branch may depend upon a result that the CPU doesn't even have yet. It won't have it for several instructions. So it takes both branches. It actually forks, and both branches of execution are taken because we want to keep these cores as busy as possible. And at some point in the future, the result of the operation will be known, which the branch depended upon, and then the CPU says, oh, okay, we keep the results down this speculative branch and discard them down the other. This is the kind of stuff going on inside these machines. Well, it turns out that the branch that is more often taken tends to be taken again. And so there's even technology in current contemporary processors that learns which branches are being taken so that it can bias them if it runs shy of resources. So the point is that there's this incredibly rich database of information from instant to instant about the short-term history of everything going on. We also have the caching going on, where we're pulling data from very slow dynamic RAM into the level 3 cache, from there into the level 2 cache, from there into the level 1 cache. There's also cache watching. So there are cache hits and cache failures, counters that are running for every hit and failure. All of this rich background texture is also a function of the exact interplay of all the other processes that are running at once. We know that there's, if you look at a task manager, for example, you'll see this long list of things going on. These are all processes competing for limited resources. So they're switching back and forth, and all of the task switches are being instrumented and metered and monitored. And you've got network activity, the network interface cards, and the interrupts that they're generated are being metered. You've got the keyboard and the mouse, and just this rich source of material, and our hard disk drives, which have spinning platters and heads moving, and the instantaneous timing of how long it takes to fetch and retrieve data is a function of the exact sequence of data being fetched, which is a function of the exact priority of all the processes that are running. So anyway, you get a sense for the fact that even though on some level it is completely determined by the events, no one has control of the exact arrival time of packets. There's jitter in packet times that are a function of the instantaneous amount of data in buffers, in routers scattered over the internet that is unknowable and will never occur again. So the point is, when I look at simple-minded random number generators, I just think, wow, they missed the boat, because there is an incredible wealth of information that is available to software that cares. So in the Squirrel client, I have something called an entropy harvester, and it has probes deep into the system, acquiring data constantly from all of these systems. It periodically takes snapshots and dumps this into a large hash pool, which is constantly being stirred. And after some length of time, when Squirrel needs some entropy, and that's one of the other interesting aspects, is the rate at which systems need entropy varies. For example, a server which is establishing cryptographic connections with hundreds of thousands of users needs, it is a hungry consumer of entropy. It needs a high bandwidth of randomness in order to satisfy the individual cryptographic needs of all these connections that it's establishing. But Squirrel has actually a very modest demand. The Squirrel servers, as we said, can use a simple counter at their end to generate nonces that never repeat. So that is very low, actually zero level of cryptographic demand there. And you, on the Squirrel client, you only really need a high level of entropy when you create a new identity and when you are re-encrypting your Squirrel database. So Squirrel's demands for entropy from this entropy harvester that I wrote, it's actually the first thing I wrote for Squirrel, are very modest. And as a consequence, we're able to produce numbers that are completely unpredictable.
I love this idea of an entropy harvester, because it really comes down to, this is what you're talking about. People who are programming don't understand everything that goes into making that IDE that they see. You
Right.
understand it because you love writing in assembly, which means you understand all the things that your code is interacting with, which is why most of the pseudo-random number generators that I've played with, they might play with the clock, they might play with a few of the RTC functions that you can find in the various operating systems that you play with, but most of them they focus on making really complicated algorithms to come up with some sort of random hash. It makes so much more sense to actually reach into the hardware, into a physical system that by its nature is going to have some true randomness in it, and use things that people wouldn't otherwise use. I was blown away by the fact that you mentioned the pipeline predictor. I remember when Intel introduced that in the Pentium series, and it was one of these things of, so wait a minute, my processor's going to learn what's more efficient, and it's going to go that branch all the time. It's a genius idea to take that and say, okay, well, it's going to discard one of the pipelines. This is a metric that we can use to create some true randomness when we combine it with the other things that also happen in the physical hardware. That's fantastic. Now, we've got CR1 in the chat room saying, okay, so let me get this straight. You harvest entropy, you get yourself a really good pseudo-random number. I mean, it is still pseudo-random number, but it's a good pseudo-random number. And then you use that to make yourself a key. Is that essentially what Squirrel does?
Yes. Yes. I mean, that's it exactly. The harvester is using a pool of entropy and hashing that into a 256 through SHA 256, hashes out a 256-bit value that is the user's identity. And due to the rich source of individual bits, which are completely unpredictable and unknowable, that is, no attacker has any way of having visibility into all of the sources of entropy that we're harvesting. So Squirrel itself has an entropy pool of the past, and so it has a large state. It's not just 256 bits. It's a much larger state, which it then, on demand, hashes into a final 256 bits. And so there's just the actual granularity of the data that we're pouring into this pool is tens of thousands of bits of entropy, which we then distill into a single 256-bit identity for the user.
Steve, I got to ask, you wrote this in assembly, yes?
Yeah, yeah.
Has this been tried before? Are you the first one to take this many metrics and put it into that entropy harvester?
I think I'm probably guilty of overkill.
No, there's no overkill for this. There really isn't. No.
No, and that's just it. Is you cannot have too much. You can only have too little. And so we're at the tens of thousands of bits that is then hashed into a final 256-bit result. I don't know of anyone else who's gone to the lengths I have, but since it's important, I wanted to get it right.
And you open sourced all this. I mean, people can actually download the code and see how you did this.
Yeah, in fact, the entropy harvester I'm really proud of. And so all of the algorithms that I've designed are all in the public domain. Wow.
Wow. That's too much. Okay, now let's step a little bit forward. People are looking at this. They're saying, okay, this is a great pseudo-random number generator. I think one of the best ways to point that out is to perhaps compare it against a not-so-great pseudo-random number generator, and that would be the one that was deliberately weakened by the NSA. Can we talk about that? Because that's the old strain of how we would generate a pseudo-random number, which is have a really complicated algorithm that at some point will give you a number that is more or less random. Why is yours so different than the one that was, say, weakened by the NSA?
That's a great question. What the NIST, the National Institutes of Standards and Technology, pseudo-random number generators don't do is harvest all of this physical material. They just assume that at the high level, and you were exactly right, Padre, when you mentioned that what I've done is gone down to the physical, essentially the molecular level of the PC, where I'm extracting individual data from the processor and using the uncertainty of the arrival time of network packets and the uncertainty of the completion time of hard disk requests, and using all this physical material to produce entropy. So I have the advantage at the assembler level of that kind of material. And so I really didn't have a problem synthesizing an incredibly high quality 256-bit piece of true, absolutely unpredictable entropy. But imagine you didn't have that access. Imagine your problem was operating at a much higher level, where, for example, you had no access to time, to the uncertainty that time provides. Actually, a perfect example are those blinking lights behind me. Those are 3 PDP-8 mini computer emulations, and the pattern of lights looks very random. To the human observer, it looks completely random. It turns out it's a very bad pseudo-random number generator. It's something called a linear congruential pseudo-random number generator, LCPRNG. And if you Google that, there's a Wikipedia page that says, don't get your hopes up, because this is pretty bad. But I needed something only that looked good. It's cryptic. It's like the worst pseudo-random number generator you could imagine, purely in software. It has a current value. I multiply it by a constant and add a different constant and throw away any overflow. That's all it is. But it turns out if you pick your 2 constants well, the multiplier and the added constant, you get something that doesn't repeat until it has produced every single possible value, and it's good enough for blinking lights on a front panel. But it has an absolutely predictable pattern because you're multiplying something and you're adding something. So the goal is, if you are starved for any source of like input of unpredictability, and I wasn't when I built SQRL's entropy harvester, but if you had to operate at a high level, what could you do? How could you come up with it's like some source of randomness? Somehow, any pseudo-random number generator needs what's called a seed. You have to seed it somewhere. So from some source, you need a seed. And any Linux people who have ever watched their Linux boot carefully, they will notice that in that scroll of stuff, when Linux is initializing, there is a PRNG that is being seeded at some point, where it begins to collect some seed material. Now, the problem that most pseudo-random number generators have is that once they're seeded, they are then purely algorithmic, meaning that they just use whatever this pool that was initially established, whatever entropy it had, and they try to then produce values from that. So we have 2 things we can judge. We can judge the size and quality of this source seeding entropy, and then the algorithm which churns it. And so the problem is the if the algorithm that churns that seed pool is not really good, if there's some bias, if there's some question about the way that it works, then there may be a way to look at the output values and predict the future, because the future prediction is going to be entirely based upon the contents of the seeding pool. That is, if all you have is a bunch of fixed data and an algorithm that generates the next version of the fixed data and the version after that, if that algorithm that evolves the seed entropy is not good, then you can get some predictability. You get if you ever knew what the state of that pool was, you could predict all the future output. So the goal is you keep the random pool secret, and maybe people can see the output. And in fact, typically in use, you will see the output, but you want the output to not give you information about the current state of the pool. And then in a mature system, you have the notion of reseeding. That is, cryptographers who operate under these constraints will say, okay, we understand that over time, as we pull pseudo-random numbers out of this pool, we are inherently disclosing the information about the pool with each one that we pull. So we need to set a limit for how many pseudo-random numbers we're going to allow ourselves to take from this pool before we reseed, before we do something to get new seeding material. And so in a mature pseudo-random number generator, they will be watching how much data has been pulled from it. And for example, maybe some physical process will be going on in the background, generating a new seed pool, which they will then switch over to in order to get a fresh set of pseudo-random numbers and be able to pull that at, until they've exhausted the trustworthiness of that pool. So lots of attention has gone into this, and I think it's just fascinating.
We're speaking with Steve Gibson, who is giving us a crash course on entropy, randomness, and pseudo-randomness. We're going to come right back. We're going to wrap them up. We are unfortunately running a little bit out of time. I always hate it that time flies so quickly when I'm speaking with Steve Gibson. But before we get back to him, let's go ahead and thank the second sponsor of this episode of Coding 101, and it's DigitalOcean. Now, let me ask you something. If you are a budding developer, at some point, you're going to need to open up your services to the outside world. That means you have to stand up a server. Maybe you have to program a brand new server. Maybe you have to bring up a new operating system to make sure that your clients get served out properly. Now, you could do it the old way. The old way would be actually to buy some physical hardware and put it into a colo and then scale it up as the demands grow, and maybe move to a different geographical location as your audience migrates, as it becomes bigger and bigger. And what we find is that scaling physical hardware just isn't the right way to go. The right way to go is with DigitalOcean. Now, DigitalOcean is for developers. They've got a system that uses droplets. Now, droplets are virtual private servers that can be customized and deployed quickly to host websites, web apps, production applications, personal projects, virtual desktops, and pretty much anything else that you can think of, all with full root access. I've been using DigitalOcean for the last couple of months to experiment with some of my projects. Sometimes I just need to stand it up for a couple of hours so that I could try it on a few of my devices. I want to see what it actually does, how it reacts in the real world. Sometimes I want to open it up for a private beta. I want to hit real traffic on my servers and on my applications to see how it will interact and whether or not it will crumble under the pressure. And then occasionally, I actually want to release it. And I've done it a few times with DigitalOcean, and each time it's as simple as it can get. From the very first server to the co-loaded millionth server, DigitalOcean will give you your SSD own cloud in as few as 55 seconds. It's built for developers, and it's used by over 400,000 of them, including me. It lets you deploy and configure your droplets via a streamlined control panel or a simple API, and you get to choose your OS. Ubuntu, CentOS, Debian, Fedora, CoreOS, FreeBSD. A one-click install lets you quickly deploy apps like Django, Docker, Drupal, LAMP, GitLab, MediaWiki, Node.js, WordPress, Ghost, Magneto, OwnCloud, Ruby on Rails, and more. All servers have up to 20 CPUs, 64 gigabytes of RAM, and 640 gigabytes of SSD storage space, which means they're highly scalable to meet the demands of a rapidly growing application or business. You can deploy your servers in regions all around the world. This is one of the things I love. Rather than being in one single co-location, I can move it from location to location to location, all with gigabit speeds, 99.9% uptimes, and even my own dedicated IPs if that's what I need. You get web console access with HTML5 plus SSH, SFTP, and KVM VNC for your virtual desktops. Now, one of the things I truly like about DigitalOcean, I think it's really, really unique, is that they've got an active community. People who like the service so much that they're willing to help others. That's one of those things that sets them apart from the competitors, and one of the reasons why you should go with DigitalOcean. Now, are you running out of reasons? If not, let me give you a few more things to push you over the top. Yes, you can get set up in as little as 55 seconds. And yes, DigitalOcean has incredible and affordable, straightforward pricing, with their servers starting at only $5 per month. There's also hourly pricing available in case you just want to stand up for a little while. That means you can start at less than a penny an hour. But we're going to make it so that it's easy and really a no-brainer for you to get started. You can deploy your own SSD cloud server now for free. Visit DigitalOcean.com and create an account. Once you confirm your email and account information, go to the billing section and enter the promo code C101 for a free $10 credit. That's plenty to get started and explore what DigitalOcean can do for you. That's DigitalOcean.com. DigitalOcean.com. And once you sign up, enter the code C101 in the billing section for a $10 credit. And we thank DigitalOcean for their support of Coding 101. Now, Steve, right now I picture a lot of our audience with brains leaking out of the side of their head, yeah, doing that thing, a little going all random. But they're going to get their hands on your Entropy harvester, and I'm sure a lot of them are just they're going to be blown away by what you've done with that tool. In fact, it is such a unique tool. I'm betting we're going to start to see it pop up over and over again. What kind of advice would you want to give to the young programmer, the young man or woman, who is maybe looking at the work that you're doing with Squirrel, looking at the work that you've done with your Entropy harvester, and they actually want to start getting into the foundational mathematics of security?
I guess I would say use as low a level language as you're comfortable with. I cut my teeth on hardware and fell in love with the hardware, and so I'm still programming even now in assembly language. But I recognize that's not for everyone. But there's some understanding that is irreplaceable in programming when you get when you like grok the notion of bits, when you understand the way bits are added and the way a register has a certain number of values before it overflows, and what the carry bit is. And and some of these things that I'm talking about, I mean, yes, you don't have to know that stuff to create a web script in Java or JavaScript. You can get you can live your entire life without understanding that. But for the things that I find interesting and challenging and worthwhile, for me, the lowest level of interaction with the system is the most fascinating. And I've often published my source code, the assembly language, and I don't have a link handy at the moment, but I know I've shown it to you before, Padre, where, I mean, my assembly language doesn't look like low-level code. I've seen, hackers producing assembly language where it's just a strip of opcodes running down the left-hand side of the page, and it is truly incomprehensible. You can write incomprehensible assembly language. You can also write incomprehensible code in JavaScript. So it's not like assembler has a corner on the market for incomprehensible code, but it's possible to write beautiful assembly language that anybody can read. And next time I'm on Coding 101, I'll have a link ready, and we can put it up on the screen when you and I are talking.
Steve, I have to say that most of my code is pretty incomprehensible, so it doesn't have to be assembly. Now, we are going to have you back on the show, and in the future, once you're done with Squirrel and you've patched away the next version of SpinRite, we have an open invitation for you. So that's always there, but I know that you're a very busy person. CR1 in the chat room has expressed a sentiment that I think a lot of us hold, which is if the world was fair, you would have $1 billion for the Entropy Harvester. It's far more useful than most of the apps that most of us will pay money for. So thank you very much for your service to program kind. Sir, could I please ask you to tell the audience where they can find you? Of course, they're going to find you every Tuesday here on the TWiT TV network, live.twit.tv, 1:30 p.m. Pacific time for Security Now. And I got to say, that should be homework. If you are at all interested in programming, you need to know the aspects of security that are going to be affecting the way that you create the applications for tomorrow. And so you should be watching that show. But where else should they go if they want to find your work, your products, and of course, your code?
I'm at grc.com, Gibson Research Corporation, www.grc.com. There's a main menu at the top of the page, and just poke around. You'll find lots of fun stuff.
Ladies and gentlemen, Steve Gibson, the man, the myth, the legend, our security guru. We thank you for being on Coding 101.
Thanks, Padre.
Of course, folks, don't forget that you can find us each and every single week, normally on Mondays at about 2:30 p.m. Pacific time, live.twit.tv. If you join us on the live stream, you can watch the pre-show, the post-show, and everything in between. And as long as you're watching, why not jump into the chat room at irc.twit.tv so that you can join along. You can be part of the experiment that is twit.tv. Now, Lou Maresca will be back for the next episode. This episode should be releasing right about the time that we are at Black Hat, and next week's episode should release right about the time that we are at DEF CON. Until then, thanks to everyone here at the TWiT Brick House who makes this show possible. Of course, to Lisa, to Leo, to my TD today, Alex Grumple. It's Grumple, right? Alex Grumple? Yes?
It's Gumpel.
Gumpel, I'm sorry, Alex Gumpel, who can be found at Twitter at twitter.com/ANELF3, and I am twitter.com/PadreSJ. Until next time, I'm Father Robert Balacer. End of line.